All right, welcome. Thanks for joining. What we're talking about today is solving logarithmic and exponential equations. So it's going to be slightly different. Here, it's not going to be as conceptual or just thinking about a number. It's going to be how do we actually go through the process of solving an equation. So there are two ways that we're going to attempt to solve exponential and logarithmic equations. First is by using the one-to-one property of exponents and logs, and second is by using the inverse property of exponents and logs. So those properties that we covered in section 3.2, it's essentially applying these two properties in order to solve an equation. So we're going to go through the first 4 slides total. That's going to be sort of, a lot of example work, but it's, it's still going to be part of the notes video. So solve for x, 2 to the power of x equals 32. Now, first, we're going to use the one-to-one property here. We can do it using the inverse property, but what we're essentially going to do is say, okay, this is 2 to some power of x. The one-to-one property says that if you have two exponential functions equal with the same base, then the exponent must be the same. So I want this to have the same base. So I'll say this is 2 to the what power? So then I'm looking at 32 and saying 32 is 2 to the what power? Well, 2 squared is 4, times 2 again would be 8, times 2 again is 16, and times 2 again is 32. So that's to the 5th power. The one-to-one property says that if I have, again, two exponential functions with the same base that are equal, then the exponents must be equal. So x is equal to 5. Oops, sort of lost my pen there. There we go. Log base x minus log base 5 equals 10. So the first thing I'm going to do is sort of get x alone. I'm actually going to get this x term alone. So I'll add log of 5 to both sides. We get log of x is equal to log of 5. And at this point, we're again going to use the one-to-one property. The one-to-one property with logarithms says if you have two logarithms with the same base, the base here, even though not written, remember, is 10 for both of these. So we have two logarithms that are equal with the same base. So the arguments must be the same. X is equal to 5. All right, next, 27 to the power of x equals 81. So looking at this, there's no power on 27 that's an integer that's going to give me 81. Like 27 to the first is 27. 27 squared is something super large and not 81. But 27, that alone can be rewritten as 3 cubed to the power of x. And 81 is the same thing as 3 to the 4th. When you're looking at this 3 cubed to the power of x, keep in mind that when you have an exponent raised to an exponent, you multiply those two. So this is 3 to the 3x equals 3 to the 4th. All I did again was rewrote 27 as 3 cubed, 81 as 3 to the 4th. Now, my one-to-one property allows me to say that the two exponents must be equal. 3x must be equal to 4. So x is equal to 4/3. So that's sort of a cool thing here because it's not coming out as an integer. So it's not something that you necessarily would have thought through. You needed this idea of how I can solve and rewrite things. All right, next, looking at the inverse property. So if I have 2 to the power of x is equal to 10, the inverse property is where you can apply an exponential function or a logarithmic function on both sides in order to cancel each other out. So let's say I wanted to get rid of a base of 2. The opposite of an exponential function is a logarithmic function with the same base. So I'm going to apply log base 2 on both sides. Log base 2 of 2 just cancels, and I'm left with x equals log base 2 of 10. Now, this is not an integer. 2 to no power gives me 10, no integer power. But if I went to a change of base formula, this is the same as log of 10 over log of 2. And in a calculator, if we did that, we get approximately 3.322. So, I mean, this right here is the exact answer. If you were asked on a quiz or test for an exact answer, that would be this. This is the approximation. All right, looking at this next one, I need to get this x term alone first. So I'm going to subtract the 5 on both sides, and I'll give myself some more room. So 2 natural log x equals -1. Now, before I get rid of natural log, I'm going to have to get rid of this 2. So I'll divide by 2 on both sides. When I divide by 2, I get natural log x equals -1/2. Thinking about natural log is just log with the base of e. So now, if I'm going to try and get rid of a logarithmic function, what I do is its inverse. So I'm going to raise e to the power of both sides, because e to the power of a log base e will cancel in the same way that log with the same base of an exponential cancels. So I'm left with just x equals e to the -1/2. E to the -1/2 is the same thing as 1 over the square root of e. Remember that the negative creates this fraction, and the 1/2 power means the square root. And if you went to a calculator, this is approximately 0.607. Again, this would be the exact. This would be my approximation. Log base 3 of x plus 4 equals 0. So I subtract my 4 on both sides. I get log base 3 of x equals -4. Now again, I'm trying to get rid of a logarithm. The inverse relationship, or the inverse function to that, would be an exponential function. So I'm going to do 3 to the power on both sides. 3 to the power of log base 3 just cancels, so I'm left with x. And then I get 3 to the -4th. 3 to the -4th is 1 over 81, which I wouldn't want as a decimal. You could leave it as 1 over 81. All right, so that's solving by the one-to-one property, solving by the inverse property. Now I'm just going to do a little bit, extra so that that example's video is a little bit shorter. If I have 7 to the power of x equals 1 over 49. So I'll leave this 7 to the power of x. And what I'm going to try and do is the inverse property, because I recognize right away that 1 over 49 is the same thing as 1 over 7 squared. And the thing that creates the 1 over, or the fractional piece of this, is to have a negative exponent. So 7 to the -2nd, that's the same as 1/49th. And the one-to-one property here says the bases are the same, and these are equal, so the exponents must be the same. X equals -2. Log base x of 625 equals 4. So if I'm looking at this problem, I want to get rid of the logarithm. So I take that base and I use it as the base of an exponential function on both sides. So this is x to the power of log base x, which cancels. So I'm left with 625. And x to the power of 4, which is x to the 4th. You can either think through, or at this point, you can take the 4th root on both sides. The 4th root of 625 is going to give me x equals 5. And then last, 2/3 to the power of x equals 81/16. So I'm going to leave this 2/3 to the power of x. 81 and 16. Well, 81 is the same as 3 to the 4th power. 16 is the same as 2 to the 4th power. So this is the same as 3 over 2 to the 4th power. Now the problem is I cannot use the one-to-one property because the bases are not the same, but I can make them the same if I flip this over. So if I flip that over, what I'm doing is making a negative exponent. Now my bases are the same, so I can say that the exponents must be equal. X equals -4. So I especially would not blow off the optional video in this. It's just some more examples, but it's, some more of like the higher end, a little bit tougher ones so that you can see a little bit of those as well. Otherwise, get started on the homework, see if you have any questions, things that you want clarified.